So this is our objective. The main goal is to design a feedback control system that keeps the motor speed constant even when the load change or when there are external disturbance. As you can see, the desired speed is the target when we want the motor to maintain, while the actual speed may fluctuate because of disturbance. The feedback system work to reduce this difference and bring the actual speed back close to desired speed. This kind of control is very important in applications such as robotic conveyance system, electric car, and industrial automation where stable motor performance is needed for reliable operation.
Next, this slide explains how the closed-loop DC motor speed control system works. The process starts with the reference input, where the user sets the desired motor speed at 1500 rpm. The controller compares this desired speed with the actual speed from the feedback sensor. If there is any error, the controller sends a signal to the actuator, or we call it as motor driver, to adjust the voltage supplied to the DC motor. Then the motor changes its speed accordingly. The speed sensor continuously measures the motor speed and sends the feedback back to the controller. So this process repeats continuously, allowing the system to maintain a stable and accurate motor speed even when the load changes.
This closed-loop system regulates a DC motor speed relative to a target input. A summing junction calculates the error signal. ES equal to RS minus CS multiplied by HS. This error goes to a proportional controller with a gain of 5, generating the control signal to drive the second order motor plant. A feedback sensor with a gain of 2 completes the loop to continuously minimize error. Next, we derive the overall system transfer function to analyze its second order characteristic. Starting with the open loop transfer function, GS multiplied by HS is equal to 250 divided by S power of 2 plus 16S plus 25. We apply the standard closed loop formula. TS is equal to GS divided by 1 plus GS multiplied by HS to get TS equal to 125 divided by S power of 2 plus 16S plus 275. From the characteristic equation, we extract key performance metrics and on-damped natural frequency of 16.58 radian from Wn the power of 2 to 175 and damping ratio of 0.483 from the multiplication of 2 multiplied by damping ratio and multiplied with Wn is equal to 16. This confirms the motor control system is underdamped and will exhibit more transient overshoot.
This slide shows the theoretical performance of our DC motor speed control system. The peak time is 0.21 seconds, which means the motor reaches its first maximum speed very quickly. The settling time is 0.50 seconds, showing that the motor becomes stable in only half a second. The percent overshoot is 17.8%, meaning the speed slightly exceeds the target before settling. Overall, these results indicate that our system has a fast and stable response. Moving to the next slide, which is about the digital twin MATLAB simulation setup. After obtaining the theoretical results, we validated our transfer function using MATLAB simulation. The transfer function was programmed into MATLAB to simulate the system step response, transient behavior, and steady-state error. This digital simulation allows us to compare the theoretical calculation with the actual simulated results and verify that our mathematical model is accurate.
So this is the output that we got after we ran a MATLAB simulations, and the results were almost identical. As we can see here, the state response shows a stable underdamped second order system, which is the motor reach a rise time of 0.0968 second for peaks at 0.219 second, produce a 17.7% for overshoot and settles with 0.495 seconds, demonstrating a fast and stable response. So next we will see a comparison between manual calculations and the MATLAB simulations. So here is the comparison between our manual calculations and our MATLAB simulation that I showed before. This table shows very close agreement with only minor differences caused by rounding. This validates the accuracy of our mathematical model and confirms that the system performed as expected. So as we can see here, um, there is the small difference come from rounding in manual calculation, while MATLAB use exact numerical values. So first, for percentage of overshoot from manual calculation, we get 17.8%. Meanwhile, for MATLAB, we get 17.71%. For peak time, we get 0.21 second for manual calculation and 0.2187 for MATLAB. And settling time, we get 0.50 for manual calculation, and for MATLAB simulation, we get 0.4950
My name is Akila Farhana binti Mazman. My metric number is B1424100008. This slide shows the system stability assessment. The poles are located at -8 plus minus 14.5258 I. Since both poles have a negative real part, they lie in the left half of the S-plane, which means the system is stable. The complex conjugate poles indicate that the system is underdamped, so it responds quickly but has a small overshoot of about 17.71% before settling. In conclusion, the system is stable, has a fast response, and reach steady state with moderate overshoot. This slide shows the steady state error for three input types. For the step input, the steady state error is 0.0909, indicating good tracking performance with only a small error. However, for both RAM and parabolic inputs, the steady state error is infinite, meaning the system cannot accurately track continuously changing signals. This happens because the system is a type 0 system which has no integrator. Therefore, the system is suitable for constant speed application but not for continuously varying or accelerating inputs.
So moving on to the next slide, let's look at the system capabilities and limitation of our design. We have categorized this into three main areas: mathematically validity, dynamic response, and operational application. First, regarding mathematically validity, I am pleased to share that our model is completely validated. We conduct manual calculation and compare them directly with exact MATLAB simulation, and the results are virtually identical. This gives us high confidence in the accuracy of our theoretical model. Next, moving on to the dynamic response, the system is highly stable and fast reacting under dam response with a settling time of exactly 0.495 s. Furthermore, the controller successfully achieved rapid stabilization immediately after a disturbance, ensuring robust performance under Trojan condition. Finally, let's address the operational application and its limitation. This system is perfectly tailored for constant speed regulation. However, it is unsuitable for trajectory tracking or accelerating target. This is due to a key limitation. The system produces an infinite errors when subjected to RAM or parabolic inputs. In short, while the system is highly reliable and fast for steady state regulation, it is resist when it comes to dynamic path tracking. Last, the final conclusion, the DC motor speed control system is precise model, highly stable closed-loop architecture. It delivers rapid bound response for constant speed application, successfully validated across both theoretical and digital environment.